So before we start with any calculations or any different systems, let's first refresh ourselves on what a mole is, right? So mole is Avogadro's number of particles, or any amount of anything that is in Avogadro's number. So 6.02 into 10 to the power 23, that is Avogadro's constant. So what's so vital and what's so special about this particular number that you have here? Why do we use this 6.02 into 10 to the power 23? Why do we use this particular number for almost all of our calculations in stoichiometry and moles? So the reason we do this is because if you have, let's say we have for carbon, so carbon has a relative atomic mass of 12, right? This is its relative atomic mass. I'll write RAM, relative atomic mass, which is basically just its mass number on the periodic table. Now, it turns out if you multiply this 12 relative atomic mass, which one carbon has, every individual carbon has 12. So if you have this number of 6.02 into 10 to the power 23 carbons, so 6.02 into 10 to the power 23, 12 relative atomic mass units, you get this. You get 12 grams of carbon. And this is why mole is so widely used, and this is why we're using moles, because by using moles we get the same number, the same magnitude of our relative atomic mass. When we multiply it by a mole, we only take 1 mole of carbon, so 12 relative atomic mass units, the mass number of carbon, we get 12 grams of carbon. This is particularly why we use moles, and this is true for any element there is, right? So let's try for oxygen. For oxygen has a mass number or relative atomic mass of 16. All right, 16 RAM. This is oxygen. And then if you multiply it by a mole, if you take 1 mole, 6.02 into 10 to the power 23, you get 16 grams of oxygen. So through this, we can write a formula, we can derive a formula for the molar mass, okay? So just see this. We know the mass, the mass number of oxygen is 16, the mass number of carbon is 12. What if we were to isolate this? This is a mathematical formula, isn't it? Then the relative atomic mass of an element times the mole. So for all elements, the relative atomic mass, you take a mole of it, you multiply it by the Avogadro constant, you get the mass number, but in grams. So you can derive a formula for this. And so you just take this, we take Mr, right, as the relative atomic mass. That's how it's written on the periodic table. So Mr equals to, we wrote equals to here, right? So we take this times mole, right, over here, and we put a division. We do division. So Mr equals to the mass in grams. Okay, mass in grams, because mass by mass, they mean the mass number of the element, and this is divided by mole. So we multiplied mole here, we divided mole here, right? There's an equal or an arrow, but same thing. So for oxygen, as we did oxygen has an Mr of 16. 16 equals to 16 grams per mole. So this over here is molar mass of oxygen. Let's do carbon. So carbon was 12. So 12, this is relative atomic mass units, is 12. Remember, we get 12 grams. of carbon over here for 12 atomic mass units. So 12 grams per mole. And this molar mass of carbon. So this just means per mole of carbon, you will get 12 grams. And you can actually rewrite this in another way. And you'll see how we use it in stoichiometry. But 12 grams per mole is the same thing as per mole, you get 12 grams, right? 12 grams per mole, you get 12 grams. This is for carbon. If we do it for oxygen, it was 16 grams per mole. So per mole, you get 16 grams. It means the same thing. We just took a reciprocal. So you'll use this mostly in stoichiometry and also in empirical formula, but that is the basic concept of a mole and why we use this particular number, 6.02 into 10 to the power 23, the Avogadro's constant. So now let's move on to empirical formula. Add a few pages. Okay. Now let's go for empirical and molecular formulas. And these are just as I'll show. So I'm gonna write the formula of just two compounds. So this over here is water, and this, let's do glucose, C6H12O6. Yeah, okay. So let's start with these two. So what we've just written here is these are molecular formulas. And this is just the formula you're used to in reactions, in everywhere across. Whenever we write, generally we're writing the molecular formula. Empirical formula is something different that we'll show in a bit. But this, whenever you write a compound, the formula of a compound, you're writing the molecular formula. So for water, this is H2O. For glucose, this is C6H12O6. Now, what these molecular formulas represent is the molecular formulas represent actually is the ratio of atoms in this compound, right? The ratio of atoms. So if you think about water, so this just means there are two hydrogens for every oxygen. There's nothing beside the oxygen, so for every oxygen. Let's just write 1. So this is just the ratio, 2:1. For 2 hydrogens, you get 1 oxygen in this compound. Over here, this is glucose. So glucose just means you have 6 carbons for 12 hydrogens and 6 oxygens. Move 6 oxygens. So that's the molecular formula, or just the chemical formula of these compounds. These are just the formulas that you're used to and that you use when you write an answer or find it out. So what an empirical formula is, just these ratios. These are ratios, right? These ratios simplified, right? So if you're thinking about carbon, if we're doing empirical, we'd make this, right? Empirical, you would write, let's divide, what can we divide this? The HCF is 6, so 1 is to 2 is to 1. So the empirical formula for glucose, this is glucose, is C, and since it's 1, I'm not going to write it, H2O. This is empirical formula. So empirical formula is just the ratio of atoms that are present in the molecular formula, or just the chemical formula, simplified. Now, if you look over here for oxygen, for water, you see we have 2:1. You can't simplify this by anything further to get whole numbers. You can make, if you divided this by 2, if you're trying, and divided this by 2, you would get 1:half. And you can't have half in formulas. They have to be whole numbers, whether that's empirical or molecular. So what the molecular, for the empirical formula is it's just empirical formula. It's the simplified ratio of molecular formula. So then what is the molecular formula? The molecular formula is the ratio of the empirical formula multiplied by a number. I'll just write constant beside it. So let me explain what I wrote here. But as we saw, water doesn't have an empirical formula because you can't simplify its literal chemical formula, but glucose does, right? So if we were to start with CH2O, remember, this is empirical, to get and this is how scientists work. Actually, we find the empirical when we're trying to when we've discovered a new compound. We actually notice the empirical formula. We first find the empirical formula, and through different processes and different apparatus, you find the molecular formula. So the molecular formula was C6H12O6. Molecular. Now, what did we need to multiply? So the ratio was 1:2:1 here. And here it was 6:12:6. So to get what I mean by an empirical formula multiplied by a number or a constant is that you multiply the ratio of the empirical formula by 6. You multiply it with 6 and you get the molecular formula. So times 6 times 6. This is what I mean. So when I'm writing times 6 here, I'm just meaning that the ratio is multiplied by 6. Let me fix the color. This should be, yeah. Okay. Cool. So that's just empirical and molecular formula. Now let's do a few questions. Okay, there's a question. So fluorine reacts with, let's read the question. Fluorine reacts with sulfur to form a compound which has 25.2% sulfur by mass and a relative molecular mass of 254. They want us to find the molecular formula. So what we have is 25.2% sulfur, and we know it reacts with fluorine, so we know our two elements are sulfur and fluorine in the final compound. So let's first assume we have 100 gram in total of our compound, and this is just we just take 100 gram, just this, so that we can convert this percentage. We can just directly write 25.2 grams of sulfur. It just makes it easier. So we have 25.2 grams of sulfur. And we also have, so we know we have 25.2% sulfur. The rest percentage should be the percent of fluorine. So let me take out the calculator. So you just subtract 100 minus 25.2 minus 25.2, 74.8. So we have 74.8 grams, because you subtract that, we have 74.8% of fluorine. So you can just write 74.8 grams of fluorine. So now we have the masses of our the elements in our compound, but we can't really work with the masses. Why? You can't just take the ratio of the masses, and sometimes some people try taking the ratio. You can't take the ratio. Why? Because the mass of sulfur is going to be different for every atom. What I mean is that sulfur has a mass number of, I believe, 32. Hold on, let me open up a periodic table. Table. New tab. I didn't know. Yeah, so sulfur. Okay, I'm wrong. Sulfur had, yeah, it is 32. Fine. So sulfur has uh, a mass number of 32. So if you and fluorine has a mass number of 18, nearly 19. We'll take 19. Okay, let me actually pull up the periodic table. Cambridge IGCSE periodic table. So since these mass numbers are different, whatever, when you multiply it by Avogadro's constant, you're gonna get different. If you were to multiply it by Avogadro's constant, you would get like 32 grams. So you have a little less than 1 mole of sulfur, and if you were to multiply it by Avogadro's constant, you would get 19 grams of fluorine. So what this just basically elucidates, since elements have different mass numbers, you can't compare the mass in grams of different elements together. Okay, because the 1 gram of sulfur is gonna have a different number of atoms compared to 1 gram of fluorine. So you can't compare the atoms of you can't find the molecular formula, you can't find the ratio of atoms by finding the ratio of mass. And here is the periodic. Oh, blurry. Take it again. Okay. Paste. Yeah. Okay. So there's our periodic table, and you can see that there's 19 gram. 19 is the mass number of fluorine, and for the mass number of sulfur is 32. So let's put this on previous page. Okay, so we know so remember how at the beginning we derived that this is the MR, right? The MR over here. MR is equal to the molar mass, MR. So MR is the mass number or the relative atomic mass. MR is, and this is equivalent to the mass, the molar mass. So mass per mole, molar mass. So what you can do is you go to the periodic table and you can see that we found out the mass number of sulfur, which is 32. So what we're going to write is 25.2 gram of sulfur. And I just put by one. It doesn't change anything. Anything by one is the same thing. And we're going to put in the molar mass. So sulfur had a mass number of 32. So you're right. So we can write either 32 grams per mole of sulfur, or we could have written, if we didn't write this, we could have written, instead of this, we could have written per mole we have 32 grams of sulfur, right? Because they mean the same thing. Now what we're going to do is we're going to take this, we're going to write it like this, and I'll show you why in a second. But what this essentially allows us to do is per mole, we have 32 grams of sulfur. So now this has allowed us to cancel in our calculation. So you can see gram of sulfur here, cut this, gram of sulfur here. We can cancel from the top and bottom of different fractions when we're multiplying them, right? So that just leaves you with 25.2 divided by 32 for the moles of sulfur. So 25.2 divided by 32, you get, we take three significant figures, so 0.78788 moles of sulfur. Now let's do fluorine. So we had 74.8 grams of fluorine. Let's write that, 74.8 grams of fluorine. I just wrote 74.8. And we know its mass number is, it was 19. So since its mass number is 19 from the molar mass that we saw, for 19 relative atomic, the 19 mass number, when you multiply it by a mole, you get 19 grams of fluorine. So you can write 19 grams per mole. That's the molar mass, 19 grams of fluorine per mole. But again, see what I did here? Since I use this, I'm gonna have to multiply this and then divide by mole, and my grams won't actually cancel out. So this was wrong. Let's fix this. So per mole, 19 gram of fluorine. So we have grams of fluorine, and we can just on the top and bottom. So gram of fluorine, we cut those, and so we divide 74.8 by 19. 74.8 divided by 19, and you get 3.921 for three significant figures. That's 3.92. So we have 3.92 moles of fluorine. Okay, so that's quite a bit. So we now have our moles of sulfur and our moles of fluorine. So what we can do is we write the ratio of fluorine, of sulfur to fluorine, or fluorine to sulfur, whichever way you prefer. 0.788 is to 3.92. So this is our ratio of sulfur to fluorine, and these are the moles. Since mole is a number of atoms, 6.02 into 10 to the power 23, you can just simplify this ratio, because this is 1 mole of, this is 0.788 moles of sulfur, and this is 3.92 moles of fluorine. And we're counting atoms now, so you can simplify these ratios. So what we generally do is you divide this by 0.788, and you divide also this by 0.788, and so this would give you 1:2, and then you have 3.92 over there, so 3.92 divided by 0.788, that's 4.97. I'll just write 5. So that is 1:5. Sometimes you might not immediately get the ratio. You might still get a decimal. Say if we had 1:0.5 here, what we would do is we would multiply this by 2 and this side by 2, and then we would get 2:1. So whatever it takes to bring the fractions to a whole number. But over here we don't have that. That's not the case. We just have 1:5. So our empirical formula, we just found out, empirical formula is S1F5, sulfur fluoride. This is the empirical formula of sulfur fluoride. Now, we were asked to find the molecular formula. So we found out the empirical formula. Remember how we said molecular formula is just a number multiplied by the empirical formula? So how do we find this number that will change this ratio to this ratio? So to do that, what you have to do is you have to divide the molar mass of this S1F5 by they've given you the molecular mass of the compound, which is 254. So we have to find the molecular mass of this sulfur fluoride. So to do that, you just write this. So molecular mass of S1F5, and I'm just going to write EMP for empirical. So sulfur we established was 32, and fluorine was 19, so 19 into 5. Let me just cross-check with the periodic table. 19 times 5, sulfur was 32. So 32 plus 19 into 5, that is 127 mass numbers, or relative atomic mass units. So 127, and we've been given that the true molecular mass of the compound, is 254. So what we do to find this conversion factor, this number, what we do is we divide 254, the molecular mass, by the empirical mass. So this was empirical. So 254 divided by 127. Let me just write that this over here is molecular mass by empirical mass. So 257 divided by 124 is roughly 2. So we found this number over here for our particular case. So now how do we determine the molecular formula? You just take the ratio of atoms. So we had S1 F5, which was for 1 sulfur, you have 5. For 1 sulfur, you have 5 fluorines. So you multiply this by 2, you multiply this by 2. If you had more, you would multiply that by 2, but we don't have more, so we don't have to worry about that. So 2 is to 10. Okay, 2 is to 10, and that is your formula. So that is the molecular formula, S2F10 of the compound. Okay, so we went slow for this one. Let's do another, and let's go faster this time. Let me add pages, add page, add page, page, add page. Okay, so that was our first empirical and molecular formula. So now let's do another one. Okay, so here's the second question. So 5.8 grams of an acid contains 2.4 grams of carbon, 0.2 grams of hydrogen, and the remaining is oxygen. So what do we know? We know we this time we haven't been given mass percent like last time. This time we've just been given the mass. We've been given a total mass, and we've been given the mass of carbon and hydrogen. And since we know the remaining is oxygen, we can just subtract the sum of 2.4 and 0.2 from 5.8 to find the mass of oxygen. So we have 2.4 gram carbon, we have 0.2 gram hydrogen, and so 5.8 minus 2.6, that's 3.2 grams of oxygen. So now we just multiply this by their molar masses to get the moles, the number of moles. So the molar mass of carbon is 16 grams per mole. So grams of carbon. GC means just grams of carbon. So grams of carbon cut. 2.4 divided by 16. 2.4 divided by 16 is 0.15. 0.15 moles of carbon. We have 0.2 grams of hydrogen, so 0.2 gram hydrogen by 1 into, we have 1 gram of hydrogen per mole, so 1 gram of hydrogen, and again just cut gram of hydrogen, so you get 0.2 again, 0.2 mole of hydrogen, and then oxygen we had 3.2, so 3.2 into 3.2 by 1, that should wait, hold on, fix 3.2 grams of oxygen by 1, and then you had per mole of oxygen you have 16 grams of oxygen. So again, we just cancel the grams of oxygen. 3.2 divided by 16 is probably 0.2. It is. So you have 0.2 moles of oxygen. So with these moles, we can find the ratio of our empirical formula. So 0.15 is to 0.2 is to 0.2, and our smallest number here is 0.15, so we'll divide everything by 0.15, but we want to get a whole number ratio, 0.15. So what we get is 1 is to, if you divide 0.2 by 0.15, you get 1.33. 1.33. I think we can take 1 for that. You get 1.33, so you just take 1. 1 is to 1 is to 1. 1.15 is close enough to 0.2, so we just take 1 is to 1 is to 1. So now we know the empirical formula. The empirical formula is C, H, and O. Okay. I believe I made a mistake. All right, no, we're fine. So 1 is to 1 is to 1, so 0.2, 0.2. Yeah, so yeah, okay. So that is fine. CHO is our empirical. This is our empirical formula. And now we also know we found the empirical formula of the compound, CH. We're done here. They didn't ask us to find the molecular formula. If they gave us the molecular formula, we would just do what we did here, and then just multiply by a conversion factor, by a number. Okay, so that's empirical and molecular formula. Now let's do stoichiometry. So stoichiometry is what I'll show you what exactly it is, but for a brief idea, it's finding a property of something that you don't know using a chemical reaction. So let's do stoichiometry. First, we'll start with a simple question for just mass. So let me list down the formulas for stoichiometry. So there's apart from the molar mass that we've learned, there's also 2 other formulas that you need to remember, or 2 other facts actually. You don't need to memorize this. So number of moles equals to volume into concentration, and concentration can be in gram per dm cube or mole per dm cube. But this is not much to memorize. You'll see in a minute why. So this is for aqueous actually. This is for acids, and so this is for solutions. And you won't get a question that asks you for number of moles without this. And another thing you have to remember is at room temperature and pressure, RTP, 1 mole of any gas takes up 1 liter or 24 dm cube of space / volume. Okay, so 24 dm cube of space at room temperature and pressure. These are the 2 other things we have to remember apart from the molar mass that we learned. while doing empirical and molecular formulas. So let's go back. So the best way to understand stoichiometry is by doing questions. Okay, so here we have here's our first question. So our first question says this: calcium carbonate reacts with dilute hydrochloric acid to produce carbon dioxide. The equation for the reaction is shown. The relative formula mass of calcium carbonate is 100. 10 gram of calcium carbonate is reacted with an excess of dilute hydrochloric acid. Which mass of carbon dioxide is produced? This was an MCQ. So actually, what is the mass of carbon dioxide produced? So we've been given this reaction. This is nothing important. You have calcium carbonate. You have hydrochloric acid. Please ignore the sketches I've made. And calcium chloride plus water plus carbon dioxide. We've also been given the relative formula mass, or the molecular mass, of calcium carbonate, which is 100. And we've been given the mass of calcium carbonate that we have. So since we have the mass number, the total mass number of calcium carbonate, we can find the number of moles. So we have 10 grams of CaCO3 as written here, and we know the relative formula mass is, we have to find out carbon dioxide, but first we find the moles of calcium carbonate. So 100, we want to get grams, we have to cancel grams, so per mole there is 100 grams of CaCO3, and then you cut grams of CaCO3 with grams of CaCO3, and so that's just 10 by 100. 10 divided by 100 is 0.1, so you have 0.1 moles of CaCO3. You could write moles of CaCO3 here, so CaCO3. So we have 0.1 moles of calcium carbonate. Now, just like in empirical and molecular formulas, you can't just divide mass. We have to take the ratio of moles. So now, if you look at the equation, we have, for if you react one calcium carbonate, one compound of calcium carbonate with 2 hydrochloric acid, you get 1 calcium chloride plus 1 water and 1 compound or molecule of carbon dioxide. So what this means is that for we're concerned with finding carbon dioxide. So 1 calcium carbonate, you can write this as a ratio. For 1 calcium carbonate, you're going to get 1 carbon dioxide. Okay, so that's just the ratio, 1:1, and you can write this as per. So for 1 compound, you could also write per mole 1 mole of calcium carbonate, because a mole, if you multiply both sides by mole, or 6.02 into 10 to the power 23, you get 1 mole on both sides, 1 mole of carbon dioxide. So what we're going to write is, we express this as a fraction as per mole of calcium carbonate, 1 mole of calcium carbonate, you get 1 mole of CO2. And this is, you can also write this, you could write the opposite. The opposite ratio would be for CO2, mole of CO2, you get mole of CO3. So this would be the same as this will be the same as writing mole of CO2. For 1 mole of CO2, you get 1 mole of carbon dioxide. Now, since this is 1:1, you generally don't need to write this. You don't need to find out this, and you don't have to go for the next step even. You could just write directly that you're going to have for 0.1 moles of calcium carbonate, you're going to have 0.1 moles of carbon dioxide. But in the case that it isn't, I want to show how to do this. In the case that your ratio is different, so we know we had let me write 0.1 mole calcium carbonate, and we know the ratio of our moles. So we are gonna put carbon dioxide on the top. We're gonna take this one, right? Because we can hold on, calcium carbonate, so that we can cancel out our calcium carbonate, our mole of calcium carbonate. So calcium carbonate, and see, mole of calcium carbonate. Oh wait, hold on. Just write this. 1 mole of carbonate, and mole of calcium carbonate, mole of calcium carbonate gone. 0.1 into 1 is just 0.1 mole of CO2. So we produce 0.1 mole of CO2. Now the question asks, what is the mass of carbon dioxide produced? So to find the mass, again, we use the molar mass. So we know the 0.1 mole, we have 0.1 mole of CO2, and we'll just put by 1 here, and we'll multiply it by the molar mass of carbon dioxide, or the molecular mass of carbon dioxide. So the molecular mass of carbon dioxide we're not this time, since we have mole over here, we're gonna put mole at the bottom. So we have carbon is 16 and carbon is 12 and oxygen is 16. So 12 plus 16 into 2, that gives you 44. So you have 44 mass number. The mass of carbon dioxide is 44. So when you multiply it by an Avogadro constant, you get 44 grams of CO2. Now, per mole of CO2. So now we can cancel the mole of CO2, and you get 0.1 into 44, you get 4.4, and we see we have grams here. So gram of CO2, and this is our answer. So this was stoichiometry. We just found the mass. This was the molar mass. This was generally the molar mass formula. Now let's do. We have 2 other formulas, so we'll see how to do those. So let me go to another question. This one's a bit lengthy. So the question says some salts can be made by titration. In a titration experiment, 20 centimeter cube of aqueous sodium hydroxide reacts exactly with 25 centimeter cube of 0.100 mole per dm cube of sulfuric acid to make sodium sulfate. Calculate the concentration of aqueous sodium hydroxide, over here, aqueous sodium hydroxide, in gram per dm cube using the following steps. Now, I've hidden the steps. I'm not showing the steps. Because if you can work without the steps, you can actually complete any stoichiometric formula. So we have the volume of aqueous sodium hydroxide, but we need to find for the concentration of aqueous sodium hydroxide, we have to find the mass per unit volume of aqueous sodium hydroxide. And if you think about it, we have the volume and the concentration of sulfuric acid. So for the formula, number of moles equals to volume, number of moles equals to volume into concentration. We can get the moles of you can get the moles of sulfuric acid. You get the moles of sulfuric acid, and then that mole, using stoichiometry from the ratio, you can find the moles of sodium hydroxide, and that mole, you convert the moles of sodium hydroxide to grams of sodium hydroxide, and since you know the given volume of sodium hydroxide was 20 centimeter cube, you just put the you convert this. We have to convert centimeter cube, but okay. Enough talking. Let's start doing this. So moles of sulfuric acid, so H2SO4. This. So to find this, we have our let me so we have the volume and the concentration of sodium hydroxide. So 25 centimeter cube of H2SO4 by 1, and the concentration was 0.100 mole per dm cube, 0.100 mole, and per dm cube by dm cube. So immediately you'll notice a problem. dm cube and cm cube, we have dm cube and cm cube, so we have to convert our units, because dm cube and cm cube are not the same units, so we can't cancel them. So 25 cm cube is, if you divide 25 by 1000, you get 0.025 dm cube of H2SO4, and we'll just put by 1 so that it's a fraction, into 0.100 mole per dm cube. Back on, you can cut dm cube and dm cube, and so if you multiply, you'll be left with moles. See, there's moles here. We have, since we cut dm cube, we have moles left here, so 0.025 into 0.100 should give us our moles. So 0.025 into 0.100. So this equals to 0.0025 moles of H2SO4. So we found out our moles of H2SO4. Now we need to find the moles of sodium hydroxide. So you can see our ratio is 2:1 for H2SO4 and NaOH. So what we can write is 0.0025 moles of H2SO4 by 1 into, and we saw the ratio. The ratio was 2:1, so for every 2 moles of NaOH, you have 1 moles of H2SO4. You could have written it the flip way. You could have written it 1 mole for 1 mole of H2SO4. You have 2 moles of NaOH. But notice we want to cut the H2SO4, so we put H2SO4 at the bottom, and so you just cut moles of H2SO4, moles of H2SO4, and you multiply 0.0025 into 2, you get 0.005. 0.005 moles of NaOH, sodium hydroxide. So that is our moles of sodium hydroxide, and we know that we have 20. We reacted 20 centimeter cube. That's the volume of sodium hydroxide. 20 centimeter cube of sodium hydroxide. So you had 0.005 mole per. This is the concentration of sodium hydroxide. 20 centimeter cube. Now, the question asked us to give our answer in grams per dm cube. So we have to convert the top over here to grams, and this over here to dm cube. So how do we do that? So again, since we have 20, so let's just do the bottom first. 20 centimeter cube is gonna become, if you divide this by 1000, you're gonna get the value in dm cube. And if for the mass, the mass in grams of NaOH, what you do is you multiply this by the molar mass. It's actually better if we don't do a fraction here. We just do it individually. So let's just find out 0.005 moles in grams. So we have 0.005 moles. So let's look at the periodic table. Sodium's mass. Sodium has a mass of 23. So sodium has 23. We're finding the mass. 23 plus 16 plus 1. So 23 plus 16 plus 1, that's 40. So you get 40 grams of NaOH per mole, and we have 0.005 moles. So we cut moles. So 0.005 into 40 equals to 0.2 grams of NaOH. And 20 centimeter cube to dm cube, to do that, you just divide this by 1000. So 20 divided by 1000, 0.02 dm cube, or liter. So you have this is our concentration, 0.2 grams of NaOH per 0.02 dm cube. Okay, and we can actually further this fraction. We can make this a round figure. So we had 0.2 grams of NaOH per 0.02 moles, 0.02 dm cube. So you can change. So you want to make this a whole number, and this is the smallest number. So you multiply this by 100, and this by 100. Right? So if you multiply that by 100, you get 2 dm cube, and 0.2 becomes 20. It becomes 2.2 into 100 becomes 20 grams. H, and you can just simplify this to 10 grams of NaOH per dm cube. So that was the concentration formula, and we have one remaining formula, which is, we found our answer, by the way. They asked in grams per dm cube, we wrote in grams per dm cube. The answer, this is the answer, 10 grams. So one last formula, that is For stoichiometry, at room temperature and pressure, 1 mole of any gas takes 1 liter or 24 dm cube of space. So let's do a question for that. Okay, so the question asks us, determine the volume of CO2 gas given off when excess we don't have to worry, is Mg carbonate is added to 25 centimeter cube of 0.400 mole dm cube HCl at room temperature and pressure. All right, so off the top of the bat, you can see we have the volume and concentration of HCl, so we can find number of moles from there. We have to determine the volume of carbon dioxide. You can ignore this. You can try without this. It's better to be able to do it without steps given. So we can find, and using the moles of hydrochloric acid, we can find the moles of carbon dioxide. And with the moles of carbon dioxide, we will be able to find the volume using the third formula. So first, let's find our moles of hydrochloric acid of HCl, right? So we have 25 centimeter cube, 25 centimeter cube of HCl, and you have 0.400 moles of HCl per dm cube. We don't need to write moles here, but I just wrote it. So first things first, we can't cross 25 and 25 with dm cube because cm cube and dm cube are not in the same unit. So we convert cm cube to dm cube. So 25 divided by 1000 to get it. We get it in dm cube. So 25 divided by 1000 is 4.025 dm cube. HCl by 1 into 0.400 mole, 0.400 moles of, we don't need to write HCl here, per dm cube. So now you can cross your dm cube, dm cube, so 0.025 into 0.025 0.025 into 0.400, that gives you 0.01. 0.01 moles of HCl. Okay, so let's add a few pages. So now we have our moles of HCl, and if you look, okay, we're back. So if you look at the chemical equation, for every 2 hydrochloric acid compounds, or 2 molecules of HCl, from the reaction, you will get 1 molecule of carbon dioxide. So for every 2 moles of HCl, you're going to get 1 mole of carbon dioxide. So our ratio is 2, we write down there. So 2 is to 1. HCl is to 1 CO2. And you can represent this as, or you could write for every 1 carbon dioxide, you get 2 HCl. Since you want to put HCl at the bottom so we can divide it, you'll just, for every mole of CO2, you get 2 mole of HCl. And what we do is we take this fraction, okay, let's stay here. Okay, so we had 0.01, 0.01. This is our rough 0.01. Zero point 0.01 moles of HCl by 1 into 1 mole of CO2, 2 mole of HCl. So you can see that you can cut the moles of HCl, moles of HCl. So 0.01 divided by, or divided by 2 into half is the same as divided by 2 is 0.005, I believe. 0.01 divided by 2.005. So we have 0.005 moles of CO2, right? Moles of CO2 is remaining, so 0.005 moles of CO2. So 0.005 moles of CO2. So we found out the moles of CO2. Now we have to find out the volume of CO2 in centimeter cube. They asked us for centimeter cube in particular. So our formula, and you'll notice over here, we have room temperature and pressure. So at room temperature and pressure, let's just first write 0.005 moles of CO2. So the formula or the fact was that at room temperature and pressure, the volume of 1 mole of any gas will take up 24 dm cube of volume, or 1 liter of volume. So 1 mole of any gas. So what we can write, since we want to find out the volume, 24 dm cube is the volume. So per mole of CO2, right? That's the fact in fractions. The way we went up to, right? At room temperature, 1 mole of any gas takes up 24 dm cube of volume. So per mole, you're going to take up 24 dm cube. So what you'll notice, we can cancel the moles of carbon dioxide. You could have even written per mole, this fraction, all the fractions you can write reciprocals of. Mole of CO2, you get 24 dm cube per mole of CM3. But we don't need to do that since we want to cancel carbon dioxide. You don't need to do that. So moles of carbon dioxide, they cancel each other. So 0.005 into 24, 0.12 dm cube. We have dm cube up here, so 0.12 dm cube of carbon dioxide. So now they asked us in centimeter cube. So 1 dm cube is about 1,000 centimeter cubes. So 0.12 into 1,000 would be 120 centimeter cube of CO2. Let me just check. Yeah. So you have 120 centimeter cube. That is our answer. So those are the 3 formulas you use in stoichiometry. Now we're going to get into the last topic, that is percentage yield. and then we'll do a few miscellaneous ones. By miscellaneous, I mean ones that don't have any specific rule or formula. You'll see what I mean. Okay, so percentage yield. So let me take out right. Percentage yield. So let me take out the question. Um, okay, got the question. So there's stoichiometry here. This is basically just another stoichiometry question. You'll see what I mean. So the question says we have 32 grams of sulfur dioxide, SO2, reacts completely with oxygen, molecular oxygen, O2, to produce 28 grams of SO3. They are asking for the percentage yield of SO3. Okay, so for percentage yield, as soon as we see percentage yield, what we have to do is for every time you're given percentage yield, you're going to be given the mass of a product, right? These are products. Everything on this side of the arrow, the right side of the arrow, is products, and these are reactants. So you're always going to be given the mass of a product. So here you've been given the mass is 28 grams of SO3, and what we're going to do is initially we're going to ignore this. We're going to ignore this, and we've been given the mass of SO2, the reactant. So what we're going to do is we're going to perform stoichiometry and find out the mass of this, even though we've been given it, find this mass by ourselves. So so we have SO2. So SO2, let's sulfur was 32, I believe. Let's look at the periodic table one more time. Okay, sulfur is 32. So we're good. Sulfur 32. So 32 grams of SO2 by 1, and the molecular or the molar mass of sulfur dioxide. Sulfur is 32, oxygen is 16, so 32 plus 16 into 2 is just 32 plus 32, 64. So you get 64 grams of SO2 per mole. So you can cut the grams of SO2, and 32 by 64 is half, I believe. So you have 0.5 moles of SO2. So we have 0.5 moles of SO2. And now let's look at our ratio. We have 2 is to our ratio. So for 2 molecules of sulfur dioxide, you get 2 molecules of sulfur trioxide. So 2 moles, you get 2 moles. So you can just write. I'm just gonna write 0.5 moles of SO3. So we know our moles of SO3. We saw how to get the moles of with the moles using stoichiometry before. I just skipped that process now to save some time. So we have our moles of SO. We know our moles of SO3 now. So now we just find the mass of SO3. So 0.5 moles of SO3 by 1, and its molar mass is going to be 16 into 3 plus 32, which is going to be 80. So you have 80 grams per mole, 80 grams of SO3 per mole of SO3. So you can cut the moles of SO3, 0.5 into 80 is 40 grams of SO3. So we found out from the information given this mass of SO3, right? So this is theoretical mass. This is the maximum. This is what you should get. You can call it maximum or what you should get, etc., etc. So this is our theoretical mass. And if you look back at the question, we were given what we ignored at first. We were given 28 grams of SO3. We were given that we got 28 grams of SO3 after performing the reaction. So we should have gotten 40 grams of SO3, but we got 28 grams of SO3. So this is our yield. Yield is like the output, crop yield, right? So what you get out. So we got only 28 grams out of. So to find the percentage yield, what we have to do is the formula is the actual, or the yield, true yield, or just the mass of the reactant that is given to you, true yield by the theoretical true yield, or mass, theoretical yield or theoretical mass into 100. So we got only 28 grams out of what we should have gotten 40, and you do this into 100. So 28 by 40 into 100, that is exactly 70%. Do another 1%. And we'll do it a bit faster this time. So not always they're going to ask you to find the percentage yield. They could even give you the percentage yield. Let me just show. So this is our question. The Haber process is a reversible reaction. Reaction has a 15% yield of ammonia, but volume NH3. Okay, so first things first, we've been given uh, the moles of hydrogen. We have been given our moles of hydrogen, and we actually have been also given the percentage yield of our reaction, but we'll see this later. First, the question asks which volume, or it should be what. This is an MCQ. What volume of NH3 measured at room temperature and pressure is obtained by reacting 0.75? So first, what we have to do is find the volume of ammonia gas. So we have 0.75 moles of hydrogen, 0.75 moles of H by 1, and let's look at our ratio. So our ratio of hydrogen to ammonia, so this our ratio of hydrogen to ammonia is 3:2. So for free hydrogen, this should be H2, 3 moles of hydrogen moles H2, you get 2 moles. You get 2 moles, or 3 moles of H2, you get 2 moles of NH3. 3. So you cut moles of H2, 0.75 into 2 by 3. 2 by 3. So we get 0.5 moles of NH3. Okay? And now we know that it's at room temperature and pressure. So since it's at room temperature and pressure, 0.5, we can find out the volume, 0.5 moles of NH3. And let me just write here that the answer has been N is in cm cubed. So 0.5 moles of NH3. And the formula or the law was that any 1 mole of any gas takes up 24 dm cube of space. So we want our moles here, per mole of NH3. We don't have to write NH3, but I'll write it. Mole of NH3, 24 dm cube of space. So moles of NH3, mole of NH3, 0.5 into 24 is 12 dm cube of NH3, ammonia. We could have written 25 dm cube of NH3, and that would keep the NH3 there. So 12 dm cube of NH3, and we convert this to centimeter cube. So 12 from dm cube to centimeter cube, you would multiply by 1,000. So 12,000 cm cube of NH3. So you have 12,000 cm cube of NH3. But remember, at the question said the reaction has a 15% yield of ammonia. So this is important. 15% yield of ammonia. So they gave us the percentage yield. So what you have to do is 12,000 by 1 into 15 by 100 to get the actual output. 12,000 into 15 by 100, you get 1,800. There was cm cube here. So 1,800 centimeter cube of NH3. And this is the answer. Okay, so now we're going to do miscellaneous questions. They don't have any formula in particular, but you have to understand the concept that we've just done. They're based on that. So let's go for our miscellaneous questions. So first, start with the big one. Okay, so this question over here. This question says find the percentage composition by mass, right? By mass. This is important. By mass of hydrogen in CH3COOH. So what this means is that they want to find out like the percentage, the mass of hydrogen, how much of hydrogen makes up the total mass of this, and you find that in a percentage. So what you do first is we see there are 4 atoms of hydrogen here, 3 and 1, 4. So 4 into 1 equals to 4 hydrogens. And we see carbon, there's 2 carbons, and we find the total total molecular mass. This was mass of hydrogen, 4 into 1, 4. And total molecular mass is, so we have two carbons, so 12 into 2 plus 4 hydrogens, so 4 plus 2 oxygens, so 2 into 16. That will give you 12 into 2 plus 16 into 2 plus 4. That gives 60. So this has a relative molecular mass of 60. Okay, so this has a relative molecular mass of 60. This has a relative molecular mass of 4. So they wanted the percentage composition by mass. What we have here is just RMA. RMA. So to find the mass, what we have to do is we use the molar mass ratio to find their masses. So for hydrogen, for these many hydrogens, it's going to be 4 grams per mole. Because we have 4 hydrogens, so 4 grams per mole. If you have 4 hydrogens, you're going to get, and you put it into the molar ratio, you're going to get 4, for 1 hydrogen, you get 1 gram. So for 4 hydrogens, you get 4 grams in a mole. And for this, so we input 60 relative atomic mass units, right? Let me just go to the first page. So we had 12 here, but we're inputting 60. So 60 into mole is going to give you 60 grams, right? So let me go back. So you have 60 grams per mole, and these are both in moles. So what we do now is, so hydrogen is 4. So since we're both in moles, we can just divide this by 4 grams per 60 grams, and then we do into 100 for the percentage. So 4 by 60, and then into 100. That gives 6.7%. So that is the percentage molecular mass. So we have one last question, and this is a pretty simple question. It won't take too long. This is the question. So it says Buckminster fullerene is a simple molecular form of carbon. The relative molecular mass of Buckminster fullerene is 720. Determine the number of carbon atoms in one molecule of Buckminster fullerene. So first, let's understand what we have. We have the relative molecular mass, right? So the mass number combined of Buckminster fullerene is 720. We know it is made of only carbon. So this you can almost easily just write 720, so relative atomic mass units divided by the relative atomic mass units of carbon, which is 12, you get 60. So there are 60 carbon atoms because one carbon atom has 12, one C atom has 12 RAM, relative atomic mass units. So there are 60 carbon atoms. And you could actually also find this using the first formula, the molar mass formula. You could derive this. So let me show how you derive that. Okay. This is empirical. So over here, remember when I showed you the reciprocal, you can write 12 gram per mole as mole per 12 gram. So what we had was mr equals to 12 gram per mole, right? So 16 gram per mole equals to, so let's write over here. You had the mr, so this was for carbon. For 12m, the relative atomic mass units is 12 gram per mole. So when we flip this, you have to get the reciprocal on both sides. 12 gram per mole. Sorry, mole. So if we want to get mole per 12 gram, so for 1 mole you get 12 grams. Yeah, you get 1 by 12 over on this side because you're getting the reciprocal on this side, so you get the reciprocal on this side. And this 1 by 12 is this. You'll just see we just did that. 1 by 12 is the same as just dividing by 12. And that's what we did in the Buckminster-Fullerene example. We just divided by 12 relative atomic mass units, the MR. So, and we had 720 RAM, so relative atomic mass units, so the relative atomic mass units cancel out and they leave you with the atoms of carbon. So that is stoichiometry and that is moles.